Hey everyone, I'm Hemant Bhanawat, and we have Sonal with us. Sonal and I come from performance engineering team here at Yugabyte. So welcome to this DSS presentation. In this presentation, in this session, we will be talking about the scaling of Yugabyte to 150K warehouses. So Yugabyte is now able to scale up to 150K warehouses using the TPC-C benchmark. We will be talking about various areas in this presentation. Yeah, so the agenda would be we'll first talk about the TPC-C overview and how it is implemented, just to give you the build the context here. Then we will jump on to the details of the 150K run. So while talking about the 150K run, we will see what was the setup that was used. We will also look at the results that we achieved, and the more important part would be the different important metrics, how YB is actually performing with the disk, with the CPU and other aspects when it is running at such a large scale. So that is what we will be discussing when we go into those slides for 150K run. Okay, so to start with, let's see what is TPC-C benchmark. So TPC-C is a OLTP benchmark, which is used widely by the databases which deal with OLTP workloads. Uh, TPC-C benchmark basically simulates an order entry environment for a wholesale part supplier company, right? So there is this company which has got these bunch of transactions going on. For example, there are orders being created or orders being delivered. Then there are recording the payments, checking the order status, checking the stock levels. So all these type of transactions are happening in a very concurrent manner on a single database, right? And across and by various different operators. So here, each warehouse, when we say in TPC-C, has got 10 operators. These operators are actually doing these data entry operations. They might be doing any one of these transactions. And when they do this transaction, there are about 10 operators in a single warehouse. And the warehouse is a way to scale. So when you say that we have about 150K warehouses, that means you have about 1.5 million operators working together to just enter the data, right? And maybe check the status of the data. So this is how the whole setup is. But the when we have to compare the performance, we actually look at how many number of new orders were processed per minute, right? So that is a metrics that we look at when we are looking at TPC-C results. So that is the metrics. So there is a theoretical transactions per minute that can be achieved as said by the TPC-C standard. So that is a theoretical limit that one can achieve. uh, we cannot reach to that level because the theoretical level assumes that the database is responding back in 0 milliseconds, right? So the what we achieve, any database might achieve, is to a certain efficiency. So when we say that Yugabyte has achieved X amount of efficiency or X percentage of efficiency, it means is that we have reached to the X percent of TPMC that Yugabyte has done as compared to the TPMC that would have been done in a theoretical as compared to the theoretical number. Now, this benchmark is designed to scale just as the business expands and new warehouses are created, like I already said. Okay. Now, why TPCC, right? TPCC is one of the most accepted databases, one of the most accepted benchmarks for OLTP databases. It's a vendor neutral approach. There is a very good standard that is defined. It's in a very clear manner. The standard has been defined, how the transactions need to be carried out, what are the different number of threads. So that way, it is a very well defined, well structured benchmark. Also, it is very realistic, right? In terms of it actually simulates a company which is doing these kind of stuffs. And to be honest, we see many such customers doing similar kind of running similar kind of workloads like TPCC. Yeah. So that's about the TPCC benchmark. Let's quickly talk about how this has been implemented, right? So like I said, in TPC-C, for every warehouse, we have 10 operators who are doing the data entries. So which effectively means that we have 10 different threads, which are doing these requests simultaneously. So if we are simulating a 150K warehouse setup, basically we have about, maybe this is a mistake here, we have about 1.5 million terminals and threads, right? So for any warehouse, we have about 10 threads, and in a 150K warehouse scenario, we will have 1.5 million threads working simultaneously or doing the simultaneous simultaneous uh, concurrent operations, right, or simultaneous transactions. Each thread, like I said, each thread emulates an operator. Now, TPC-C assumes that an operator, TPC-C says that since an operator is going to be a human being, it adds up certain keying time and think times for the operator. So what the thread, the implementation thread, which is actually doing TPC-C, has to take care of keying times and thinking times. What that means is that every thread waits for certain duration, for certain seconds, so that the operator, saying that it is the keying time, then it does the transaction, and then it gives some time for thinking. So the operator has got a result back, and now he's thinking about the result. So that is the thinking time. Um, when there are 150 million threads, most of these threads are spending their time in keying and thinking. Only some percentage of them are actually making calls to the database. Now, each thread, after keying, will pick up a transaction. That transaction can be a new order transaction, or a payment transaction, or order status, stock level, or a delivery transaction. And TPC-C has defined that how much percentage of these transactions should be part of that complete mix, right? So for example, new order is about 45% of the total number of transactions that happen. Uh, and efficiency, like I said, efficiency is a metric which is derived from TPMC, and it tells us how close YB or any other product will gets to the theoretical latency, right? So theoretical latency is something that is already defined by TPC-C standard, and how close you can get to it, because theoretical latency has been calculated assuming that the database will take about 0 millisecond for any query. Okay, that was more about TPC-C. From YB perspective, how has been our TPC-C experience, right? With TPC-C, we have been seeing that TPC-C is a CPU bound thing, right? We consume CPU a lot more than what we consume IO, right? Although they are not comparable, but we are not CPU bound. We are CPU bound and not IO bound, right? When we are running a TPC-C kind of workload, right? So and same is true for a lot of other workloads, and that is why a lot of focus goes into how the CPU usage can be reduced, because as we reduce the CPU usage, we will be able to perform much better with TPC-C and with actual workloads, right? So things like we try to figure out how many RPCs are being fired in a certain transaction. Can we reduce them? Can we reduce the locking that we are doing at certain places, right? So that we can have better utilization. How to reduce the number of failures, because every time you have a failure because of a transactional conflict, uh, that will cause you a loss of an event in transaction per minute, right? So if you lose a transaction, an event in transaction per minute, your efficiency will go down, your TPMC is going down, right? So that we also look at how we can reduce these transactional conflicts. We try to move as less data as possible, so that again, the same reason. And obviously, another important aspect is we definitely are trying to do more and more better reporting. This better reporting is helping us to figure out where the bottlenecks are, or where are the areas where we can do better, right? So this is how we are going with TPC-C. Now I will give the control to Sonal so that she can talk about our 150K run. Sonal, over to you.
Thank you, Hemant. Hello, everyone. Myself, Sonal Agarwal. At Yugabyte, I work on the performance profiling of YugabyteDB. So we at Yugabyte are happy to announce the successful run of 150K warehouse on YugabyteDB. And before we disclose the results here, let me just walk you through the cluster setup we did for 150K warehouse. So for 150K warehouse cluster setup, we have used 75 node universe. And we have created this universe using the YB platform. Out of these 75 nodes, 3 nodes are master nodes, and the remaining 72 nodes are actually the T server nodes. The universe is created with a replication factor of 3, and it is created in a single availability zone. All these nodes are hosted on AWS C5D 12x instances. And just to add more about it is like YugabyteDB's performance is not based on the type of instance, but it depends on the number of cores of the instance that we have. For example, we did a 100K run on C5D 12x large machines, which had 60 nodes, and also on AWS C5D 9x large machines, which had 56 nodes. And in both the runs, we got the similar efficiency. Talking about the number of clients here. So we had 60 individual client nodes, and each of these clients were connected to all the T servers in the universe. For the 150K run, we loaded about 49.5 TB of data. This is the replicated data size, and it took around 11 hours to load this data into the cluster. After this data was loaded, and before we ran the execute phase, we manually performed compaction for all the tablets across all the servers. And why this is important is because compaction helps us reclaim the disk space due to overwrites and deletes that have already happened. And since TPC-C being a mixed workload, where new data is entering continuously entering the engine continuously, reclaiming of the disk space becomes important. Yeah. So the next one is client-side setup. Yeah. So on the client-side setup, we had. So when we say that the client nodes, so these are the TPC-C client nodes are actually the nodes that are hosting the Yugabyte TPC-C client TPC-C application. And for a single client, we can, for 2,500 warehouses, we can use a single client. But if we have more than 2,500 warehouses, we recommend using multiple clients. Though we say 2,500 warehouse, but we are also able to scale to 2,700 warehouses per client. For 150K run, we have used 60 clients. These clients are hosted on AWS C5 2x large instances. And so for all this setting up 60 clients and installing TPC-C on all these machines is a very tedious job. So we use our in-house performance tool. So performance automation tool that takes care of end-to-end client setup and executions. With just few clicks, we are able to run the TPC-C on any scale, and so it saves the efforts and times of our time. Next is, so here we see is the overview page of our platform UI for the universe that we created for TPC-C 150K warehouse run. This platform UI shows us that we are running 75 this is created on 75 nodes hosted on the C5D 12x large instances. It also gives us information about the CPU utilization, overall CPU utilization in the universe, the operations happening, and also the data volume that is being loaded in the system. Also, it gives us information about the health check while all the nodes are healthy, up and running, or is there any issue? Yeah. So next is the tables view that we have. So this Oh yeah. So for universe, we have the tables view, and for TPC-C we have 11 tables. This UI shows us actually the view for each size of the table and on which key space it is, and like the status of the table with respect to the replication factor, and also yes. So after that, the next is the nodes. So this is also one of the UI tabs that we have for the universe. This nodes UI actually shows us the different information about the nodes, like the um, processes running on the node on the VM. So for the first three nodes that we see is we have the master as well as T servers running, but these T servers are disabled. So we see that these are not hosting any data here in the SST file size. So this is just a few of the nodes that we are showing here, and the rest of the nodes we see are having the actual data, and we can also see the uncompressed SST file size here. Along with that, when the operations are happening, we see the read and write throughput for each node in the read write ops per second column. Okay. So the next is the actual results that we have for TPC-C. So we are happy to announce that we did not only have a successful run, but we also achieved more than 99% of efficiency. The average throughput across the client nodes was around 1175 with a total TPMC of 12.76 million. Yeah, the average latency across the transactions was around 142 seconds. The CPU utilization across the nodes was around 80%. And the failures that required retry were, for new orders, it was 0.26%. For payments, it was around 1.4%. And delivery, it was 0.10%. So these transactions were retried, and they were successful after we had a retry. So this is the transaction latencies that we have. So this is the P90 average latency, P99 latency, and the count for the transactions that have been executed throughout the run. For new order, we had 766 million new order transactions with the average latency of 123 milliseconds and the P99 latency of 696 milliseconds. For payment, it was 721 million, 0.9 million new payment transactions with average latency of 83 milliseconds and P99 latency of 265 milliseconds. Delivery, it was 67 million. Order status, it was 68 million. And stock level, we had 68 million transaction executions. Yeah, so the platform shows us. So there is a metrics page on the platform UI. So we will be seeing the different information that platform UI, this metrics page on the platform UI shows us. So the one of the is the CPU utilization in the node level. So this CPU utilization, as we can see across the run, is 80%, 65% is user CPU utilization, and 15% is the system CPU utilization. So, and one thing, talking about the trend that we see in the beginning, in the lines of the graphs here, the trend that we see is because we are running the TPC-C clients one after the other with a delay of minimal time between each client. So that's why, as and how the clients are getting started, we see that this is increasing, and this uniform graph that we see is after all the clients have actively started working. Yeah. So after the CPU utilization, we have this SQL operations. This in this SQL operations, in this SQL operations, we see that we are, if we add up all the SQL operations, we see that we are executing around 950K SQL operations. And if we see individual operations, we see that the select operation has a throughput of 310K with average latency of 6 milliseconds. The update operation throughput is 490K with average latency of 4 milliseconds. The insert operation throughput is around 125K with average latency of 18 milliseconds. And also the delete operation throughput is 20K with the latency of 9 milliseconds. So the next one we have is the read and write latencies. So these are the read and write average read and write latencies across all the nodes in the 72 nodes we have. So if we see the number here, the read latency is 3 milliseconds, and the average write latency is 8 milliseconds. Yes. So the next part that we see in the metrics page is the cache hit and miss. So as we see in this graph, we have most number of hits and very less misses here. So this is because we have our blocks caches implemented, and because of this, we have this product optimization, which helps us read more data from the cache, and like the hot data from the cache, and very less from the disk. Transaction conflicts and retries is then one of the graphs that are seen in the metrics UI page. And so basically in payments transaction, one particular warehouse can be more updated from multiple threads. So this can increase the chances of conflicts. So we retry these conflicts, and after retries, these conflicts go away. So whatever we see is these transaction conflicts here. Compaction. So as like compaction is a background activity which is continuously going on, and this helps us reclaim the disk space. So as like we said earlier, like TPC-C is a mixed workload, and reclaiming of the disk space is also becomes very important. So this activity is happening in the background continuously. Okay, so we have had a look on the metrics side of the node, and which helps us analyze and look at the run results. So, but we have one more thing is the TPC-C output, and I'll just walk you through the format of the TPC-C output that we get. So the first part is the results part that we have, and this results parts actually has the TPMC efficiency and throughput for of each. So this result TPC-C output is for each client, and we actually average the numbers for each client and get the average efficiency for when we have a multi-client run. So TPC-C efficiency and throughput for this client is being shown in the results tab. After the results, we have the latencies, and this latencies also includes the attempts. So we have different types of transactions executing in TPC-C: new order, payment, order, delivery, and stock level. So the count of each transactions that have executed, and the average latency for each transaction has been displayed here with their P99 and connection acquisition latencies. So the next part here is one thing that we know, so in the latencies, one thing that we note is the new order transaction latencies. So if this scales up or scales down, this is one area where we look and identify if there is some performance degradation. Yeah. So yeah, and the next part is the failure latencies. So failure latencies are actually the amount of the amount of time spent for the failure transactions to run. Yeah. So again, this is for at per transactions that is being executed. So, yeah. The next is so worker task latencies, like as told by Hemant, there are different phases of each transaction, like fetch, work, keying, operation with retry, and thinking. So this is the split up of each transaction that is executed, and this is just a snippet to show that we display, we capture, we display the time spent and in each phase. And again, if there is a performance degradation, it helps us to look concentrate on an area where we, that may have caused the degradation in the performance. So the last thing is the retry. So we have seen that we display the failure transaction failure count and everything. So we actually retry those transactions, and the number of retries attempts we have specified is 2. So if, at first, if the here we see that we had around 5,200 failures of new order transactions, but when we retried, we had 357 failures of new order transaction, and in retry to again the count dropped to 26 transactions. So similarly, we have the retries for payment and delivery transactions as well. And as we see here, after retries, these transactions are succeeded. And that's it from us. Thank you.
Thank you everyone for your time. We would be happy to take any questions around TPC-C or scaling of Yugabyte to TPC-C. Thank you.